So we will ignore wire capacitance in this class. We'll just worry about transistor capacitance. And let's first look at BJTs, where BJT capacitance comes from. And what you have for a BJT is you have the top layer of silicon, and then you have the emitter, you have the base, and you have the collector. And for a BJT, you always have the, oh, one more, mark the substrate down here. You always have a layer of depletion region right there, because it's always off. And when you're talking about the transistors we're using in this class, we want to be in the forward active region. Oh, that's big. In the forward active region. So in the forward active region, only junction that's forward bias that's conducting is the BE junction, and the BC junction is also off. So you have a depletion region here, and this junction right here is on, so there's no depletion region between B and E. And what happens when you have a depletion region is that the doped silicon, that behaves like a conductor. The depletion region behaves like an insulator. And so your collector right here, here's a conductor, insulator, conductor. This actually acts like a parallel plate capacitance. So you have capacitance here because you have a depletion region, and then you have capacitance here because of the depletion region between the base and collector. So the boundary between the collector and the substrate acts like one giant capacitor. The junction between the base and the collector, that acts like a second giant capacitor. Now you say that the BE junction, that's forward bias. So if this was a NPN, this PN junction would be off or not conducting. This, and then the substrate's also P. This PN junction would be off and not conducting. But this, in the forward active region, this PN junction is on and it is conducting. So you say, there must not be any capacitance. Just like with the transistors that we used to, when we needed something that behaved like a large resistance. It wasn't really a resistor, but it behaved like a large resistor. In this case, this junction right here, even though it's conducting and there's not this depletion region, this still has capacitive behavior. What happens is when you change the voltage on the base or the emitter, electrons have to travel, and it takes time for them to travel, and so it actually looks like there's a capacitor here. So that also, even though there isn't what looks like a parallel plate capacitor, there's capacitive behavior. So in a BJT, there are only 3 capacitances. There's the CCS, there's the CBC, or CB, not picky, and the CBE. So there's only 3 capacitances that you see in a BJT. I'll post this handout, but each one of those capacitances has an equation. Your base emitter capacitance is, it's got 2 parts to it. The capacitance between the base and emitter, you have one that has to do with the depletion region, and that the equation for that is 2 times the area of the emitter. So somebody has to give you that, and it's not in the model file, times the zero bias depletion capacitance of BE. And this value right here, just like so many of the other values that we've seen, is up here in the model file. That's CJE. Okay. And there's actually another, just like when, in that force bias junction, the base emitter junction, when you change a voltage, it takes some time for the electrons to travel, and that is this TB, which is your base transient constant, and it is this one right here. So I should highlight that. Okay. So if you needed to find the base emitter capacitance, the capacitance between the base and the emitter, you do 2 times the area of the emitter, which somebody has to give you, times the zero biased junction capacitance, which is this one, CJE, and then you'd add it to this transit time, which is this TF, times IC over VT, which is just your GM, and that would give you the capacitance between the base and the emitter. If you want to find the capacitance between the collector and base, now you need the area of the collector times the zero bias BC junction capacitance, and that is this one. So that is the value that goes here, and then that's 1 over 1 plus VCB, so that's your actual voltage across there, and then this. These values, I need to figure out what this is in the model file. So I'll go back, probably just looking at it. This is VJE, no. I have to go back and figure out where these come from in the model file. But that would go in there. And then there's another constant right here, and I believe MCB is one of the M's here. One of these two. I'll look that up and make sure to fix this document before I post it. But having those values, you can find the collector substrate capacitance and collector base capacitance. And I did a little example here. So here's a side view, cross section of a BJT. Here's a top view, and here's the emitter area right here. It's 0.6 micrometers wide and 2.4 micrometers tall. So when you find remember, if you're finding the base emitter capacitance, have this equation here, which is 2 times the area of the emitter. So the area of the emitter is 0.6 times 2.4. You come down here and look at the equation. There's your 0.6 times 2.4, and there's the 2 that's out in front, and then you have to multiply that by the zero bias CJE right here. Okay. And then plus, you've got the transit time, which your TF right here, times your GM, which is IC over VT. And it's generally femtofarads. Femtofarads or picofarads. And then to find the capacitance between the collector and the base, you have the area of now the base, and the area of the base is this square right here. I guess it should be actually 3.2 times whatever this width is, which is 1.4. So this should be 3.2 times 1.4 times, I left the equations here, times the zero bias junction voltage, and I apparently am missing the denominator on this, so I'll fix that. And from that, you can find those capacitance values. Okay, next thing is for MOSFETs. MOSFETs are a little more complicated. They have actually 5 capacitances. Remember, the BJTs only had a capacitance between the base emitter, the collector base, and the substrate collector. So there were only 3 capacitances. For a MOSFET, there's 5. And you, if you're on the gate, notice you've got 3 capacitances connected to the gate right here. The gate capacitance is the sum of these 3. And I've given you the equations for those 3 in the saturation region. Your capacitance, this center capacitance, you can look up in this table depending on what region of operation you're in. But remember, we're always trying to be in saturation. So to find this capacitor value, you'd add up everything in this row, which is just 2/3 Cox WL effective. Let's go to another slightly easier one. So this one is just your gate channel capacitance, and then there are these capacitances over here on the edge of the gate. It's because the gate overlaps the drain and the gate overlaps the source, and that little overlap, physically, it makes a parallel plate capacitance. And you have, so the gate is a conductor, and then the insulator between the gate and the silicon's an insulator, and then the drain or source, those are conductors. So you get an actual parallel plate capacitor. And to find the capacitance of either one of those, you have this gate source overlap times W and gate drain overlap times W. And this gate drain, gate source overlap, those you will find again in the model file. So on the drain side, when the gate overlaps the drain, you take the width of the gate and just multiply by this. On the source side, you take the width of the gate and multiply it by this, and you have the capacitance for the overlap. And then again, the gate capacitance is the sum of these 3 things. This table gives you this capacitance. This equation here, the gate source overlap times W, give you these 2 capacitances. There's just these 2 capacitances left. And those are the most complicated. That capacitance this is a 3D picture of the source. This is the gate right here. We're just interested in the source or the drain. This has a subscript of S, so I'm assuming they're taking this as the source. Yes, it says source right there. Okay, so it's actually kind of shaped like a box, and the sides of the box have capacitance, and the bottom of the box, so underneath the box, has capacitance. And you calculate those separately. The bottom of the box, you find the area, so whatever this length is, and right here it says LS, length of the source, times the width of your gate. So the source, you consider the source width right here the same as the gate. That's how much the gate is overlapping your source. So you have the width here times this LS, which tells you the size of this, and this distance right here is not necessarily equal to the length of the gate. So the gate length and the source length are usually not equal. So somebody has to give you this source length. So the area of this is LS times the width of your gate, and let's zoom in a bit. So here's LS times the width of your gate, That's the area of the bottom, and you multiply that by Cj. And guess where you find Cj? It's in the model file. So you find the area of the bottom of the source and multiply by that. And now you just have to add in the capacitance from around the sides of the source. And these are called sidewalls. And you don't count, we just did this overlap where the gate overlaps the source, so that capacitance has already been calculated. So we just look at 3 sides of the source. So the side closest to me, the side farthest from me, and the side that's not under the gate, you add those 3 together. And the way you do that is you have 2 sidewalls and 1, I guess, width. And so you take 2 times, since you have 2 sidewalls, you do 2 times LS. And then you have this one side on the side it's not under the gate, that's W. And you add those together. And if you add those together, what you get is the distance if you walk all the way around these 3 sides that aren't under the gate. So it's the length around, if you took a tape measure and wrapped it around the outside here, that's the length you get. And you multiply that by CJSW. Guess where that is? That is in the model file. Okay. So the drain and source capacitance is the sum of the sidewall plus the bottom. So that's what this equation is. The capacitance of the gate are the overlaps plus the channel. The overlaps plus the channel. Actually, I need to correct something I just said. Okay, I'll correct it right now because I think this is a good place. But if you are asking for all the capacitance that's on the source, you have this capacitance, this equation that we just looked at. But also, if you're just sitting on the source and saying how much capacitance do I see, you still see the overlap capacitance there. So the total capacitance on the source is the bottom capacitance, the sidewall capacitance, and the overlap capacitance. That's if you're on the drain, you see that. If you're on the gate, you see these overlap capacitances too, but I'm getting my words messed up here. If somebody asks you for the capacitance on the gate, you look at what capacitances are connected directly to the gate and you add those up. If you're looking at the capacitance for the source or the drain, you look at what capacitances are directly connected to the source. So that would be this one and this one, not any of the others. None of the others are directly connected to the source. If you're asked for the drain capacitance, you just have 2 capacitances for the drain here. Doesn't see any of these other 3. So this picture right here should be really helpful. It'll tell you which capacitances to add up. And again, the drain, you see the overlap, but you see it from this side. If you're on the gate, you see the overlap, but you're seeing it from the other side. But just not paying attention to that, just whatever capacitance is connected directly to the terminal of interest, you just add up those capacitances. So this has 2, gate has 3, source has 2.